So this lesson here, we want to just introduce one concept, and it's the idea of the scalar product. And the reason why this scalar product is important is because it really gets us to one of the key elements here, and that is finding an angle between two vectors. Okay? Finding the angle between two vectors. And we can do this in 2 dimensions or 3 dimensions. Okay? But in order to do that, we have to do this scalar product. Okay? Now, there are a couple of different types of multiplication when we have vectors. We're looking at 2 of them. One we already did, the scalar multiple, where you're just multiplying a vector by a constant, and you just, if you're multiplying by 2, you just double each of the components. If you're multiplying by 5, you just multiply each of the components by 5. Alright? But here what we're dealing with is a different type of multiplication. It's called the scalar product in a lot of the IB stuff. It's also commonly called the dot product, and that's because the notation is just this dot. It doesn't show up real well here, but it's just this dot here, u dot v is how we read that. And you'll notice here that what we're doing is we're taking the 2 x components and multiplying them together. We're taking the 2 y components and multiplying them together, and then we're just adding them together. And the reason why this is called the scalar product is because our end result is not going to be a vector. It's going to just be a number. Okay? It's just going to be a scalar. Alright, so in this case here, if I were doing u dot v, I would do 3 times 6 plus 4 times 2. And I'd have 18 plus 8, which is 26. Okay? It's relatively simple. Then we have u dot v with 3 dimensions. And it's the same concept, we just have a third component that we have to do it with. Okay? So we're going to do 5 times 4. Plus 7 times 6, plus 11 times 5. Okay, so we have 20 plus 42 plus 55, so we get 97, 117. Okay? And that's all there is to it. It's a really simple thing, but it's a really powerful tool because what we're going to use it for, we'll look at some different properties here that they look more complicated than they are. But then what we're going to use it for is to actually find the angle between different vectors. Okay? So for example here, one of the things that we want to know about dot product is that dot product is commutative. It doesn't matter if it's u dot v or v dot u. You're going to get the same answer. Okay? Another thing, and this one is a little less obvious, but so I want to illustrate this one. If I dot a vector with itself, I actually end up getting the magnitude squared. Okay? I want to actually show that here to you with vector u. Okay? If I did a u dotted with a u, I would have 2 times 2 plus 8 times 8, right? So that would be 4 plus 64, which is the square root, or not square root, which is 68. Okay? If I were to do the magnitude of u, I would be doing the square root of 2 squared plus 8 squared. You guys seeing it now? Okay. Well, the square root of 2 squared plus 8 squared is the square root of 4 plus 64. So if I then did the magnitude of u and I squared that, I have the square root of 68 squared, which obviously is just 68. Okay? And that'll work every time, no matter what the components are. You'll get the same thing. Okay? Another relatively simple thing here is that if I have a constant times a dot product, I can either do the dot product first and then multiply that by the constant, or I can multiply one of the vectors by that constant and then do the dot product. For example, if we, well, in this case we have u and v and k is 8. In this case, I probably would not want to multiply u by 8 first and then have to do the multiplication there. I could do the dot product first and then multiply it by 8. But just to illustrate that we can, let's see that one, okay? So we have 8 times u dot v, okay? So u dot v, let's actually put them in there. The vector 2, 8, dotted with the vector 4, 12. Okay, if I do that dot product, I have 2 times 4 is 8, plus 8 times 12 is 96. Yeah. Okay, so that's 104. So 8 times 104 would be 832. Good. All right. Now, if I had done 8 times u, first of all, I would have had 16 and 64 dotted with a 4, 12. Okay? So I would be doing 16 times 4, which is 64, plus 64 times 12. Okay? Which would be 640 plus another 128. 768? Yeah. Okay. Now if I add those together, I get 820 plus 12, so 832. Get the same thing either way. In this case, waiting to multiply by the 8 was useful. However, if that instead of an 8 was maybe like a 1/2 or something, that would make my number smaller. Or a 1/4, I could multiply the 412 by the 1/4 and make it into a 1/3, and then it's smaller numbers to work with. Okay? So, again, it's a matter of knowing the different properties and just being able to use them to help yourself out whenever you can. Okay. Yeah?
Final answer is 832.
Yeah.
You don't have to square root it.
No, that's it.
I mean, I just square it. Like the last one was radical 68 squared.
Well, that was just this property we were trying to illustrate. The dot product of u dotted with itself equals the magnitude squared. That was the property we were trying to show. That's why we squared the magnitude, to show that these were equal. 68 was 68. Okay? And then the last one is another pretty simple one. It's just a matter of the distributive property. The distributive property works when you have dot multiplication. So u dotted with the result of v plus w is the same thing that I would get if I did u dot v plus u dot w. Okay? So again, you could use this if it would keep your numbers smaller to go ahead and do 2 separate dot products, then you can certainly do that. If it would be more useful to go ahead and add the vectors first and then do the dot product, then you can do that as well. Alright, so it's kind of up to you. So let's look at this main application. Alright? One thing that's a little bit tricky with this is the fact that this formula as it's written here does not show up in your formula booklet. Okay, and actually it's not called the angle between 2 vectors. In the formula booklet, it actually gives you 2 formulas for the dot product. One is the one we already looked at. The other one is that the dot product u dot v equals the magnitude of u times the magnitude of v times the cosine of the angle between them. Alright? All they did was multiply both sides of the equation with the magnitude of u and magnitude of v. So the challenge is that they call this the formula for dot product.
So we need to know how to draw the unit circle.
You need to know what?
How to draw the unit circle.
You should know the unit circle, yeah. You're going to use that a lot throughout this year, okay? Alright, so we might have a little bit of review to do. That's okay, that's every year we do this, so. You'll be pros by the end of the year. So, the challenge here is that if you're relying on your formula booklet, you got to make sure you understand your formula booklet isn't going to have a formula for angle between vectors. It has this, which you can use to find the angle between two vectors. And the reason for it is this, okay? In a lot of real life applications, we don't necessarily have the component vectors to then go get the angle. A lot of times in real life, we have an angle because it's something visual we can actually measure, and we might have magnitudes. So then we could go backwards and figure out a dot product, okay? But as we'll see later on, we have worked with, how to use a magnitude and direction in order to get the components in 2 dimensions. But here, just to illustrate as we close, I would need to do the dot product of u and v here. I'd need to find the magnitude of each of those, and then simply plug those into our formula. Okay? Alright, so picking up where we left off, we have this formula for the angle, and I told you that this shows up in your formula booklet as the dot product of 2 vectors. But this is the formula that we're going to use to find the angle between the vectors. Okay? So let's actually do that with the 2 vectors that are given. Let's take a quick look at how we would use this formula. Alright, so I don't know what exactly these look like. This could be vector u, and this could be vector v. This is in 3 dimensions. Alright, so again, it's hard to draw 3 dimensions on a flat surface. But the angle we're looking for, if I have 2 lines that are intersecting, or 2 vectors that are starting at the same point, I can always draw a single plane through them. Okay? So we end up having, on this single plane that I've drawn through them, we have this angle theta. Okay? That's the angle that we are looking for. Alright? So, the first thing I need to do is find all 3 parts of our formula. Okay, so first of all, I need to find this dot product. Alright, so u dot v is going to equal, and who remembers how we do this?
5 plus 4. No, 5 times 4 plus.
Yeah, 5 times 4.
Plus 7 times 6.
Good.
4 times 5. 4 times 5.
Yeah, 11 times 5. Okay. So now that's 20 plus 42 plus 55, and if we add all that together, we get 97, which is 117. Okay. Now we need to put that over the magnitude of vector u and the magnitude of vector v. Whoops. So let's do the magnitude of vector u here. Square root of
5 squared plus 7 squared plus 11 squared.
There you go, okay? So when we do 25 plus 49 plus 121, 121 and 49 is going to be 170 plus 25, that's the square root of 195. Okay? And that's 39 times 5, which are both primes, so that doesn't simplify. Okay? And then we do the magnitude of v. Okay? So the magnitude of v, same thing. 4 squared plus 6 squared plus 25 squared. Not 25 squared, 5 squared, which is 25. Alright, so 25 and 16 and 36. 16 and 36 would be 52, and 25 is 77. So that's square root of 77. Okay? So, finally, we can now say that the cosine of this angle theta between u and v is going to be the 117 over the square root of 195 times the square root of 77. Couple of things with this. Please be careful when you're putting this into your calculator. If you put 117 divided by radical 195 times radical 77, what's going to happen?
And then do 117 over 195, and then do that times the radical 77.
Yeah, it's going to multiply by the radical 77. So, you said we need parentheses, okay? Please don't mess up on the calculator stuff, okay? That's why I tell you guys as we're doing stuff in class, have your calculator with you to make sure that you are learning these little things and whatnot as you go along. Okay? Okay, so we have that, and we get that into the calculator, and then how do we solve for theta?
Do you do first?
You get .95.
Did someone do this? Did you get 0.95?
Well, you did 117, and then you have to do like inverse cos.
Yes, you're gonna do inverse cosine, like you guys are saying.
I got .954,823.
Okay?
And then I'm gonna do inverse cos.
And you do inverse cosine. And what would that end up equaling?
17.3.
17.288.
17.288. So if we do 3 sig figs, 17.3. Now that is in degrees, right? Your calculators are in degrees. Now, in IB, sometimes we'll switch back and forth. In some cases, we will do radians. In some cases, we'll do degrees. Okay? If we were, basically just my point is there, be careful to look at the context of the problem. And this one we weren't, it said between 0 and 180. Okay? So we would make sure that we're using degrees. Okay? So please just make sure your calculator's in degrees. Now, I want to use this opportunity to think about the cosine. A little bit of trig review. Okay? If you recall from our unit circle for cosine, in the first quadrant, cosine was what? Positive or negative?
Positive.
Positive. In the second quadrant,
Negative.
it's negative. In the third quadrant, it's
Negative.
negative. And then the fourth quadrant, it's positive. Okay? All students take calculus, so all of them and cosine are positive in the first and fourth. Okay? Now, another thing along with that is at 0 degrees, cosine equals 1. At 90 degrees, cosine is 0. At 180 degrees, cosine is negative 1. And then at 270 degrees, cosine is back to 0. Alright? Because cosine is the x-coordinate on the unit circle. Now I say this for a couple of reasons. First of all, notice our dot product is what's going to determine whether the whole thing is positive or negative. Because magnitudes are always positive. Okay? So, since our dot product was positive, we know our answer should be an acute angle. It should be between 0 and 90. Okay? If our dot product was negative, that means we'd be in the second quadrant, somewhere between 90 and 180. Okay? Then we have a 90-degree angle. Okay? If the angle is 90 degrees, that means that the cosine of theta equals 0. The magnitudes are not going to be 0. So that means our dot product would have to equal 0. Okay? The dot product, u dot v, equals 0. You can stop right there. You don't even have to find the magnitudes. You can say automatically theta equals 90 degrees. Okay? Every time. Now, the term for that is the term orthogonal. That is a vocabulary term that you should be familiar with. Okay? Two vectors are orthogonal if the dot product is 0.
Which means one of them or both of them have to be 90 degrees.
The angle between them is 90 degrees. So like up here, these would be angled so that the angle there was 90 degrees. Okay? Okay, yeah, one more thing here. If I have vectors that are added, this is one thing that you have to be a little bit careful with, okay? What you're going to be doing here, the formula assumes the vectors have the same starting point. So basically, if I were to find theta and just did the formula just like I had, I wouldn't actually be finding this angle here. I would be finding the angle as though I drew vector v from there.
Yeah.
The formula is going to give me this.
Gives you 180, right?
Exactly. Okay? The angle that I would be getting would be the supplement to the angle between these when they're added. Okay? So, I know it's maybe there's small arrowheads here. So notice the direction of these vectors. Okay? So, we could say this a number of different ways here. The notice v is still going to be parallel to itself. So theta and this angle down here, this is going to be 180 minus theta. Okay? But this is what the formula gives. So you have two options. Use the formula and then subtract from 180. Okay, so that's option 1. Use the formula and subtract from 180. The other option, option 2, is if we had this right here, instead of doing the angle between u and v, if I want them to start at the same point, what I could do is v, and then this would be negative u. Now, will making it negative u change the angle, or change its direction at all? No, it's just going the opposite direction,
Okay, yeah.
okay? Which is 180 degrees, opposite direction. So then, the angle I'm looking for would be the correct angle that the formula gives. Okay? So use, in this case, a negative u in the formula.
What's the formula?
The formula we just did, the dot cosine theta
Yeah.
equals the dot product over product of the magnitudes. Okay? So you have two options there. It's up to you.
Is it always gonna be negative u? No, right? So I'm just gonna.
It's gonna be the opposite of whichever one came first in the addition. So here it was u plus v, so you would do negative u. If it was v plus u, you'd do negative v. Okay? And actually, remember vector addition is commutative,
Mhm.
so it actually doesn't matter which one you make negative. I could have done negative v in the
Yeah,
formula.
I was gonna say that.
Yeah, that would work as well. Give you the same thing.